Welcome to True.
Windsor Upper Dam, a monument to American engineering innovation, a complete documentary. Chapter 1, The Birthplace of Vermont. In the rolling hills of southeastern Vermont, where the Connecticut River traces its ancient path along the border of New Hampshire, there stands a monument to American ingenuity that has quietly endured for nearly 2 centuries. The Windsor Upper Dam, also known as the Ascutney Mill Dam, represents more than just a feat of engineering. It is a testament to the resourcefulness of a young nation, the determination of a frontier community, and the transformative power of harnessing nature's resources. To understand the significance of this remarkable structure, we must first journey back to the birth of Windsor, Vermont itself. The town's story begins in the tumultuous period of colonial America, when disputes between colonial governors created opportunities for ambitious settlers seeking new frontiers. In July of 1761, colonial governor Benning Wentworth of New Hampshire issued a charter for the township of Windsor. Wentworth had a keen interest in this region, not merely for territorial expansion, but for its abundant natural resources. The vast stands of white pine that covered these hills were particularly valuable. These towering trees could be fashioned into ship masts, a lucrative commodity for New Hampshire's coastal shipbuilding industry. The timber trade promised wealth, and Wentworth was eager to claim it. However, the charter itself did not immediately attract settlers. The French and Indian War still raged through the northern colonies, and the wilderness of Vermont remained dangerous and largely unexplored. It would be 3 more years before the first permanent residents would arrive. In August of 1764, Captain Steele Smith and his family departed from Farmington, Connecticut, and ventured north into the wilderness. They were pioneers in the truest sense, clearing land along the Connecticut River and establishing the first permanent settlement in what would become Windsor. By the close of 1765, approximately 16 families had joined them, constructing rough-hewn log cabins and beginning the arduous work of transforming forest into farmland. The location was chosen with strategic purpose. The Connecticut River provided a crucial north-south transportation route at a time when overland roads were scarce and in generally poor condition. The river served as a highway for commerce, allowing settlers to transport goods and receive supplies from established communities to the south. But it was another waterway that would prove instrumental to Windsor's development and prosperity. Mill Brook, a modest stream flowing through the southern portion of the township, possessed characteristics that made it invaluable to an emerging community. This unassuming brook would become the industrial heart of Windsor, powering the mills that would transform raw materials into the necessities of civilized life. Chapter 2, The Industrial Imperative. In the pre-industrial world of the 18th century, water power was the lifeblood of manufacturing. Before steam engines, before electricity, before internal combustion, the turning of a water wheel provided the mechanical force necessary for industry. From the ancient Roman aqueducts to the medieval monasteries of Europe, civilizations had long understood that flowing water could be harnessed to save human labor and increase productivity. For a frontier community like Windsor, 2 types of mills were absolutely essential to survival and growth: sawmills and grist mills. Sawmills transformed felled trees into lumber for construction. Without them, every board had to be laboriously cut by hand with pit saws, a backbreaking and time-consuming process. Gristmills ground grain into flour, converting the harvest into edible food. Without them, each family would have to grind their own grain with hand mills or mortars and pestles, an exhausting daily chore. As early as 1767, several sawmills and gristmills were already operating along the banks of Mill Brook in Windsor. These early mills were modest affairs, utilizing simple wooden water wheels connected to mechanical systems through belts and gears. The principle was elegant in its simplicity. Water striking the paddles of a wheel created rotational force, which could then be transferred to a saw blade or grinding stones. However, these mills faced a critical limitation that threatened their viability and, by extension, the economic development of the entire region. Mill Brook, like most streams in the mountainous terrain of Vermont, experienced dramatic fluctuations in water flow throughout the year. During spring snowmelt and after heavy rains, the brook would swell into a rushing torrent, but during late summer and early fall, when rainfall was scarce, the stream could dwindle to barely a trickle. During these periods of low water flow, the mills stood idle. Water wheels that should have been turning sat motionless. Saw blades that should have been cutting lumber fell silent. Grinding stones that should have been producing flour gathered dust. The unpredictability of water supply created an unreliable industrial base, hampering construction projects and threatening food security. This was the fundamental problem facing Windsor in the early 19th century. The community had the mills, the skilled workers, and the raw materials. What it lacked was a consistent source of power. As Windsor grew and prospered through the early 1800s, this limitation became increasingly untenable. By 1820, Windsor had achieved remarkable prominence for a frontier settlement. The town had become known throughout New England for its precision manufacturing, particularly in the production of firearms, tools, and mechanical devices. The presence of skilled craftsmen and the development of innovative manufacturing techniques had earned Windsor a reputation as a center of American industry. Yet the mills along Mill Brook continued to suffer from irregular water flow. During dry seasons, production slowed or ceased entirely. Business owners found themselves unable to fulfill orders. Workers faced uncertain employment. The economic potential of the community was constrained by the whims of weather and seasonal precipitation patterns. The solution was clear to any engineer or millwright of the era. What Mill Brook needed was a reservoir. By constructing a dam upstream, water could be impounded during periods of high flow and released gradually during dry periods. This would create a steady, reliable water supply year-round, allowing the mills to operate at full capacity regardless of seasonal variations. But recognizing the solution and implementing it were two entirely different challenges. Building a dam of sufficient size to regulate Mill Brook would require capital, engineering expertise, and considerable organizational effort. Someone would need to take the initiative, secure funding, navigate property rights, and oversee construction. Chapter 3: The Visionaries Behind the Dam. In 1828, a group of Windsor's most prominent citizens and business owners came together to address the chronic water shortage plaguing Mill Brook. These men were not merely dreamers or theorists. They were practical businessmen who understood that the economic future of their community depended on reliable industrial capacity. The leading figures in this enterprise included some of Windsor's most respected manufacturers and merchants. They owned mills along Mill Brook and had direct financial interest in ensuring consistent water power, but they also understood that their individual prosperity was tied to the collective success of the community. A dam that benefited one mill would benefit all mills downstream. These entrepreneurs formed what would effectively function as an informal development company, pooling their resources and expertise to undertake a project far larger than any single individual could accomplish. They hired surveyors to identify the optimal location for a dam, consulted with millwrights about the technical requirements for effective water storage and release, and negotiated with upstream landowners for the necessary property rights. The site they selected was approximately 2 miles upstream from the main concentration of mills in Windsor Village. At this location, Mill Brook flowed through a relatively narrow gorge, with steep banks on either side. The topography was ideal for dam construction. The narrow width meant less material would be required to span the stream. The steep banks would contain the reservoir and prevent water from spreading across a wide floodplain. The bedrock foundation appeared solid and capable of supporting a substantial structure. However, identifying the right location was only the first step. The next challenge was designing and constructing a dam that would be both effective and durable. This was no simple undertaking. Dam failures were not uncommon in the early 19th century, and a catastrophic breach could not only destroy the investment but also threaten lives and property downstream. The Windsor investors needed an engineer, someone with both theoretical knowledge and practical experience in hydraulic structures. They found their man in Ithamar Beard, a millwright and engineer whose expertise in water power systems had been proven through various projects across New England. Ithamar Beard was representative of a particularly American type of engineer in the early Republic. He was not university-trained in the European model. Rather, his education came through apprenticeship, hands-on experience, and careful observation of successful structures. He understood the properties of materials, the behavior of flowing water, and the principles of structural mechanics through practical application rather than abstract theory. Beard's approach to the Windsor Upper Dam project reflected the pragmatic engineering philosophy of his era. He would use locally available materials wherever possible. The design would be robust and over-engineered rather than minimalist. Construction techniques would be straightforward enough that local laborers, supervised by skilled craftsmen, could execute them reliably. The dam design that Beard created was classified as a gravity dam, one of the oldest and most proven dam types in human history. The fundamental principle of a gravity dam is elegantly simple. The weight of the structure itself resists the horizontal force of water pressure. By making the dam sufficiently massive and properly shaped, the force of water pushing against it would be counteracted by the dam's own weight pressing downward into its foundation. For the Windsor Upper Dam, Beard specified a structure built primarily of earth and stone, with timber reinforcement at critical points. The dam would be constructed in a trapezoidal cross-section with a broad base narrowing toward the top. This shape provided maximum stability while minimizing the amount of material required for the upper portions of the structure. The foundation would be excavated down to bedrock wherever possible, ensuring that the dam rested on the most stable possible base. Leakage underneath the dam, a common cause of dam failure, would be prevented through careful preparation of the foundation and the use of puddled clay as a sealant. The upstream face of the dam would be relatively steep but armored with stone to resist erosion from wave action and ice. The downstream face would be more gently sloped, providing stability and allowing for easier maintenance access. A carefully engineered spillway would allow excess water to flow safely over or around the dam during periods of high runoff, preventing overtopping that could erode and undermine the structure. Chapter 4: Construction and Engineering Triumph. Construction of the Windsor Upper Dam began in the spring of 1829. The timing was strategic. Spring and early summer offered the longest days and most favorable weather for outdoor labor. Additionally, starting in spring meant that workers could take advantage of relatively low water flow in Mill Brook before the autumn rains arrived. The first phase of construction involved site preparation. Workers cleared trees and vegetation from the immediate construction area and created access routes for hauling materials. The dam site was surveyed and marked with stakes and lines to guide excavation and construction. Foundation excavation was brutal, physical labor. Armed with picks, shovels, and crowbars, teams of workers dug down through layers of soil and glacial till to reach solid bedrock. In some areas, this meant excavating 6 feet or more. The material removed during excavation was not wasted. It would be sorted and reused in constructing the dam itself. Once the foundation trench was prepared, the actual dam construction could begin. The method used was essentially a refined version of techniques that had been employed for centuries. Workers built the dam in horizontal layers, or lifts, each one compacted before the next was added. The core of the dam consisted of earth mixed with clay, carefully placed and tamped down to create a relatively impermeable barrier. This earthen core would be the primary water-retaining element of the dam. On either side of the core, layers of stone rubble provided structural strength and protected the earth from erosion. The stone used in construction was quarried from nearby outcroppings of granite and schist. Typical of Vermont's geology, teams of stonemasons shaped the larger blocks for key structural elements, while smaller stones were used as fill material. The largest stones were reserved for the downstream toe of the dam, where they would provide maximum stability and erosion resistance. Timber played several crucial roles in the dam's construction. Wooden forms and frameworks guided the placement of earth and stone. Timber piles driven into the foundation provided additional stability in areas where bedrock was not immediately accessible. Wooden sluice gates controlled the release of water through the dam, allowing millwrights downstream to adjust flow to meet their needs. The spillway, perhaps the most critical safety feature of any dam, was constructed on the northern end of the structure. This carefully graded channel allowed excess water to bypass the dam during spring floods and heavy storms. The spillway was lined with stone and configured to direct overflowing water away from the dam face, preventing erosion that could undermine the entire structure. Construction continued through the summer and into the fall of 1829. As the dam rose higher, the work became increasingly challenging. Material had to be hauled up ramps or hoisted with simple cranes. Workers labored on increasingly narrow work surfaces. The physical demands were enormous, and construction camps were established near the site to house the laborers. By late autumn, the dam approached its final height of approximately 30 feet above the original streambed. The reservoir behind it had begun to fill, testing the integrity of the structure. Engineers and investors watched anxiously for any signs of leakage, settling, or structural weakness. Minor seepage was expected and accepted. Significant leaks would require immediate remediation. Through the winter of 1829 to 1830, the dam held firm. Spring runoff in 1830 would provide the ultimate test, subjecting the structure to the highest water pressures and flow volumes it would experience. When the spring melt came, the dam performed as designed. The spillway handled excess flow without incident. The main structure showed no signs of distress. The reservoir filled to its designed capacity, creating a substantial body of water approximately 2 miles long and covering roughly 60 acres. The Windsor Upper Dam was complete and operational, at a final cost of approximately $8,000, a considerable sum in 1830. The dam represented one of the most significant infrastructure investments in Windsor's history, but the investors understood they were not merely building a dam, they were building the foundation for decades of industrial prosperity. Chapter 5: Industrial Renaissance. The immediate impact of the Windsor Upper Dam on the local economy was dramatic and multifaceted. Mills that had previously operated only seasonally now ran year-round. Production capacity increased substantially. New businesses, attracted by the reliable power supply, established operations along Mill Brook. Within 5 years of the dam's completion, the number of mills operating on Mill Brook had nearly doubled. Sawmills multiplied, processing the virgin timber that still covered much of Vermont's landscape. Gristmills expanded their capacity, grinding flour not just for local consumption, but for export to other communities. New types of manufacturing emerged, taking advantage of the mechanical power that flowing water provided. One of the most significant industrial developments was the expansion of precision manufacturing in Windsor. The town had already established a reputation for skilled metalworking and the production of firearms. With reliable water power, these operations could scale up considerably. The National Armory at Springfield, Massachusetts, had pioneered the concept of interchangeable parts in firearms manufacturing during the early 1800s. This revolutionary idea that components could be made to such precise specifications that any trigger would fit any lock, any barrel would fit any stock, had transformed the potential for mass production. Windsor's machinists and toolmakers embraced these concepts and refined them further. Machine shops in Windsor began producing not just finished products, but the machine tools necessary for precision manufacturing itself. Lathes, milling machines, gear cutters, and other specialized equipment were designed and built in Windsor and sold to manufacturers across New England and beyond. This meta-industrial capacity, the ability to make the machines that made other products, represented a sophisticated level of manufacturing capability. The water-powered trip hammers along Mill Brook shaped hot iron and steel into everything from horseshoes to agricultural implements. Textile mills established operations, processing wool from Vermont's thriving sheep farms into finished cloth. Tanneries used water-powered mechanical processors to transform raw hides into leather. Paper mills converted wood pulp and textile scraps into various grades of paper. The economic multiplier effects extended far beyond the mills themselves. The workers employed in these industrial operations needed housing, food, clothing, and services. Merchants opened shops to serve the growing population. Professionals, including doctors, lawyers, and teachers, established practices in Windsor. The town's population grew substantially through the 1830s and 1840s, and its tax base expanded correspondingly. Transportation infrastructure improved to accommodate the increased industrial output. Better roads were constructed to connect Windsor to neighboring communities. Warehouses were built to store finished goods, awaiting shipment. The Connecticut River saw increased traffic, as boats and rafts carried Windsor's manufactured products to markets downstream. The dam also had important social and cultural impacts on the community. The reliability it provided allowed business owners to make long-term plans and investments with greater confidence. Workers enjoyed more stable employment and predictable income. The prosperity that flowed from industrial expansion funded civic improvements, including churches, schools, and public buildings. Education benefited particularly from Windsor's industrial success. Recognizing that skilled craftsmen required education beyond basic literacy, private academies were established to provide advanced instruction in mathematics, engineering principles, and technical drawing. These institutions produced the next generation of machinists, millwrights, and engineers, who would continue Windsor's tradition of manufacturing excellence. By 1850, Windsor had become one of the most industrially developed communities in Vermont. While agriculture remained important to the broader economy of the region, Windsor itself had transformed into a manufacturing center. The mills along Mill Brook hummed with activity throughout the year, their water wheels turning steadily thanks to the reservoir upstream. The Windsor Upper Dam had proven to be one of the most successful infrastructure investments in Vermont's history. The initial cost of $8,000 had been recouped many times over through increased industrial production and economic growth. The structure had performed flawlessly for 2 decades, requiring only routine maintenance and minor repairs. Chapter 6: Engineering Evolution and Maintenance. As the Windsor Upper Dam approached its 3rd decade of service, the inevitable effects of time and weather began to manifest. No structure, regardless of how well designed and constructed, can withstand the forces of nature indefinitely without maintenance and eventual rehabilitation. The most significant challenge facing any earthen dam is erosion. Water is remarkably patient but relentless in its ability to wear away materials. The upstream face of the Windsor Dam, despite its stone armoring, experienced gradual erosion from wave action and ice movement. During winter, ice expansion could dislodge stones and open gaps in the protective facing. Spring ice breakup could gouge and scrape the dam face. The downstream slope, though protected from direct water action, faced its own challenges. Rainfall runoff created small channels and gullies. Vegetation taking root in the earthwork could be beneficial in some respects, as plant roots help stabilize the soil, but it could also be problematic. Large trees growing on the dam face could create pathways for water seepage when their roots eventually decayed. The timber elements of the dam required regular inspection and replacement. Wooden sluice gates and their frames were subject to rot, especially the portions alternately exposed to air and water. The expansion and contraction of wood, with changes in moisture content, could cause warping and gaps. The mechanical components that operated the gates, including ropes, pulleys, and cranks, needed periodic replacement. Fortunately, the investors who had built the dam understood from the outset that maintenance would be an ongoing requirement. They established a fund specifically for dam upkeep and employed a dam keeper whose responsibilities included regular inspections, minor repairs, and operation of the water release gates. The dam keeper's duties were constant throughout the year. In spring, he monitored water levels carefully, releasing water as needed to prevent overtopping during the snowmelt runoff. In summer and fall, he managed releases to maintain optimal flow to the mills downstream while conserving reservoir capacity. In winter, he watched for ice damage and cleared spillway channels to ensure proper function when needed. Major rehabilitation work was undertaken in the 1850s, approximately 25 years after original construction. This work included replacement of deteriorated timber elements, reconstruction of eroded sections of the upstream face, and improvements to the spillway design based on decades of operational experience. The engineering work of the 1850s rehabilitation reflected advances in dam design and construction that had occurred since the original 1829 construction. Engineers now had access to better surveying instruments, more sophisticated understanding of water pressure and flow dynamics, and improved materials. While the basic concept of the gravity dam remained unchanged, the execution could be refined and improved. One significant upgrade involved the installation of a more sophisticated gate system for controlled water release. The original wooden sluice gates were replaced with better designed mechanisms that provided finer control over flow rates and were less prone to failure. This improved the ability of mills downstream to optimize their operations according to specific power requirements. The spillway was also modified to improve its capacity and efficiency. Hydraulic engineers had developed better understanding of optimal spillway shapes and configurations. By adjusting the spillway geometry, engineers could increase its discharge capacity without making it physically larger, providing an additional margin of safety during extreme flood events. Throughout the latter half of the 19th century, the Windsor Upper Dam continued to serve its intended purpose admirably. The industrial economy it supported evolved as technology advanced. Water-powered mills gradually gave way to steam power and eventually electric power. By the early 20th century, many of the mills along Mill Brook had closed or converted to other power sources. However, the dam remained important for other reasons. The reservoir it created had become a valued recreational resource. The impounded water moderated downstream flow, reducing erosion and providing more stable aquatic habitat. The dam had become part of the community's identity and heritage, a tangible link to Windsor's industrial past. Chapter 7. The 20th Century and Beyond. As Windsor transitioned from an industrial economy to a more diverse economic base in the 20th century, the role and significance of the Upper Dam evolved accordingly. The structure that had been built to power mills now served different but equally important functions. By the 1920s, most of the water-powered mills along Mill Brook had ceased operation or converted to electric power. The industrial landscape that had defined Windsor for a century was changing. Factories that once hummed with the sound of water wheels and machinery now stood silent or had been repurposed for other uses. The precision manufacturing industry that had flourished in the 19th century had largely moved elsewhere or consolidated into larger operations. Yet the dam remained structurally sound and continued to regulate Mill Brook's flow. The reservoir it created had developed into a valuable recreational amenity. Local residents used the impoundment for fishing, swimming, and ice skating. The surrounding land became informal parkland, where families could picnic and enjoy nature. In the 1930s, during the Great Depression, federal work programs provided funding for dam improvements and repairs. The Civilian Conservation Corps, which employed thousands of young men in conservation and infrastructure projects, undertook restoration work on the Windsor Upper Dam. Workers reinforced eroded sections, improved access roads, and enhanced the surrounding area. This work exemplified how New Deal programs invested in maintaining and improving infrastructure even in small communities. The dam, though no longer essential to industrial operations, still provided value in flood control, water supply regulation, and recreation. Its preservation was deemed worthy of public investment. World War II brought temporary renewed industrial activity to Windsor as manufacturers shifted to wartime production. However, this resurgence was brief. The post-war period saw continued decline in traditional manufacturing and a shift toward service-based economy throughout New England. Through the second half of the 20th century, the dam required periodic maintenance and occasional repairs. The Vermont Dam Safety Program, established in the 1970s, brought professional oversight to dams throughout the state. The Windsor Upper Dam underwent regular inspections to assess its structural condition and ensure it met modern safety standards. These inspections revealed that the 19th century engineers had built well. The basic structure remained sound, with the earthen core and stone facing still performing their intended functions. However, modern engineering analysis identified areas where improvements could enhance safety and longevity. In the 1980s, significant rehabilitation work was undertaken to address seepage issues and improve the spillway capacity. Engineers used modern geotechnical investigation techniques, including core sampling and seismic analysis, to assess the dam's internal condition. While the exterior appeared solid, these investigations revealed that internal erosion had created voids within the earthwork, a condition that could eventually lead to failure if not addressed. The rehabilitation work involved carefully excavating portions of the dam, removing compromised material, and rebuilding with properly compacted fill and modern geotextile materials that improved impermeability and structural integrity. The spillway was upgraded to handle larger flow volumes, reflecting modern understanding of probable maximum flood events. This work demonstrated the advantage of proactive maintenance and rehabilitation. By addressing problems before they became critical, engineers extended the dam's service life while maintaining its historic character. The visible portions of the structure retained their 19th century appearance, while internal improvements ensured continued safe operation. Chapter 8. Tropical Storm Irene and Modern Challenges. On August 28, 2011, Tropical Storm Irene struck Vermont with devastating force. Though it had weakened from hurricane strength before reaching New England, Irene brought unprecedented rainfall to the Green Mountain State. Between 6 and 11 inches of rain fell across much of Vermont in less than 24 hours, with some locations receiving even more. The impact was catastrophic. Rivers and streams throughout Vermont rose to record levels. Floodwaters swept away homes, destroyed roads and bridges, and caused widespread damage to infrastructure. The storm caused 7 deaths in Vermont and resulted in damages estimated at over $700 million. Small streams and brooks like Mill Brook experienced some of the most dramatic flooding. These watercourses typically had steep gradients and narrow channels, characteristics that caused them to rise rapidly during heavy rainfall. The volume of water flowing down Mill Brook during the height of the storm was estimated to be 50 times its normal flow. The Windsor Upper Dam faced the most severe test in its 182-year history. Water poured into the reservoir faster than it could be released through the spillway and gates. The reservoir level rose higher than it had ever risen before, approaching the crest of the dam itself. Overtopping, the passage of water over the top of a dam can quickly lead to catastrophic failure as the flowing water erodes the downstream face and undermines the structure. Dam safety officials monitored the situation anxiously throughout the storm. If the dam failed, a wall of water would surge down Mill Brook, threatening homes, businesses, and infrastructure downstream. Emergency management personnel prepared evacuation plans for areas that would be inundated if the dam breached. The dam held. Despite water levels reaching the extreme upper limits of its design capacity, despite the tremendous hydraulic forces acting upon it, despite its age and the centuries of wear it had endured, the structure maintained its integrity. Water flowed over the spillway at tremendous volume, but the spillway performed as designed, safely conveying the excess flow without causing erosion or damage to the dam itself. When the storm passed and floodwaters receded, engineers conducted detailed inspections of the dam. They found evidence of the tremendous forces it had withstood. Some surface erosion had occurred on the downstream face, where spray and seepage had occurred. Minor sloughing had taken place in a few locations, but the fundamental structure remained sound. The 19th century engineers had built with sufficient conservatism and factor of safety that their design could withstand an event far beyond anything they could have anticipated. The performance of the Windsor Upper Dam during Tropical Storm Irene stood in stark contrast to the fate of many other Vermont dams. Several dams in the state failed during the storm, releasing catastrophic floods that compounded the damage. Other dams were so severely compromised that they had to be breached deliberately after the storm to eliminate the ongoing threat they posed. The contrast highlighted the importance of conservative design, quality construction, and regular maintenance. Dams that had been poorly maintained or modified inappropriately were far more likely to fail or suffer severe damage. The Windsor Upper Dam, though nearly 2 centuries old, had been maintained throughout its life and had undergone appropriate upgrades when modern engineering analysis identified needs. Post-Irene repairs and improvements to the dam included reconstruction of eroded sections, enhanced instrumentation to monitor the structure's performance, and improvements to emergency spillway capacity. These upgrades reflected lessons learned from the storm and incorporated modern best practices in dam safety. The 2011 flood also sparked broader conversations about dam safety and management in Vermont. State officials recognized that many small dams, some of them older than the Windsor Upper Dam, had received inadequate maintenance and oversight. New regulations were implemented to ensure more rigorous inspection schedules and to require dam owners to have emergency action plans in place. Chapter 9. Engineering Legacy and Historical Significance. The Windsor Upper Dam stands today as one of the oldest continuously operating dams in Vermont and one of the finest examples of early American civil engineering in New England. Its survival for nearly 2 centuries, through countless storms, through the transition from industrial economy to post-industrial society, through changing ownership and varying levels of maintenance, speaks to both the quality of its original design and the importance the community has placed on its preservation. From an engineering perspective, the dam exemplifies the empirical approach to design that characterized American engineering in the early Republic. Ithamar Beard and his contemporaries did not have access to sophisticated mathematical analysis or computer modeling. They could not calculate precise stress distributions or model water flow with computational fluid dynamics. Instead, they relied on principles derived from observation and experience, on proportions and forms that had proven successful in other structures, and on conservative design that erred on the side of overbuilding rather than efficiency. This empirical approach produced structures that were often heavier and more expensive than might have been strictly necessary, but also structures with inherent factors of safety that allowed them to survive unexpected loads and deterioration. The Windsor Upper Dam was built to a standard that provided resilience far beyond its original design criteria. The dam also represents an important chapter in the history of American industrial development. The reliable water power it provided enabled Windsor to participate in the Industrial Revolution that transformed the American economy in the 19th century. The precision manufacturing capabilities that developed in Windsor, supported by the steady power from Mill Brook, contributed to the development of interchangeable parts manufacturing and mass production techniques that would reshape American industry. Several innovators who worked in Windsor during its industrial heyday went on to broader influence. The skills and knowledge developed in Windsor's machine shops spread throughout New England as workers moved to other communities and established new enterprises. The tradition of Yankee ingenuity, the combination of practical skill and innovative thinking that characterized New England manufacturing, found one of its most concentrated expressions in towns like Windsor. From a community planning perspective, the dam demonstrates the value of infrastructure investment in enabling economic development. The $8,000 invested in 1829 generated returns that extended over decades and touched virtually every aspect of community life. This leveraging effect, where strategic infrastructure investment enables much broader economic activity, remains relevant to community development today. The dam's history also illustrates the importance of ongoing maintenance and stewardship. Infrastructure does not maintain itself. Without the regular inspections, routine repairs, and periodic major rehabilitations that the Windsor Upper Dam has received throughout its history, it would not have survived to the present day. Many dams built in the same era failed or had to be removed because they did not receive adequate care. The evolution of dam safety regulations and professional engineering oversight has played a crucial role in the dam's preservation. Modern engineering analysis has identified issues that 19th century engineers could not have detected, and modern materials and techniques have allowed repairs that extend service life while maintaining historic character. Chapter 10: Preservation and Future Stewardship. Today, the Windsor Upper Dam continues to serve the community, though in ways quite different from its original industrial purpose. The reservoir remains a recreational resource. The dam provides some measure of flood control benefit, and the structure itself has historical and educational value. However, maintaining a nearly 2-century-old dam in safe operating condition presents ongoing challenges. The dam is classified as a high-hazard structure, meaning that failure would likely result in loss of life and significant property damage to areas downstream. This classification requires regular professional inspections, detailed emergency action plans, and ongoing maintenance to ensure the structure remains safe. Modern dam safety standards are considerably more rigorous than those applied when the dam was built or even when it was last rehabilitated. Engineering knowledge has advanced, understanding of hydrologic events has improved, and regulatory requirements have become more stringent. Bringing an historic dam into full compliance with current standards can require substantial investment. The current owners and managers of the Windsor Upper Dam face decisions about its future. Should the dam be maintained in perpetuity? Should it be rehabilitated to extend its life another century? Should it eventually be removed and Mill Brook returned to a free-flowing condition? Each option has implications for safety, cost, historic preservation, and environmental impact. Maintaining the dam requires ongoing financial commitment. Regular inspections must be conducted by qualified engineers. Routine maintenance such as vegetation control, minor erosion repair, and gate maintenance must be performed. Periodic major repairs or improvements may be needed. These costs must be balanced against the benefits the dam provides and the alternatives available. Rehabilitation to modern standards would require substantial investment, but could extend the dam's life significantly. Modern engineering techniques could address any remaining internal issues, improve spillway capacity to handle larger floods, and install better monitoring systems. Such work could ensure the dam remains safe and functional for another generation or more. Dam removal is an option increasingly considered for older structures that no longer serve their original purpose. Removing the dam would eliminate ongoing maintenance costs and safety concerns. Mill Brook would return to a more natural condition, potentially benefiting aquatic habitat and fish passage. However, removal would mean losing an important historical structure and would alter the landscape in ways that might not be desirable to the community. These decisions are complicated by the historical significance of the structure. The Windsor Upper Dam is potentially eligible for listing on the National Register of Historic Places as an outstanding example of early American dam engineering. Such designation would bring recognition of its importance, but might also complicate future decisions about modifications or removal. The dam also has educational value. It can serve as a tangible connection to Windsor's industrial heritage and as an illustration of early engineering practices. Interpretive signage and programs could help residents and visitors understand the dam's role in community development and its engineering significance. Environmental considerations add another layer of complexity to decisions about the dam's future. Modern understanding of stream ecology recognizes that dams, even relatively small ones, can have significant impacts on aquatic ecosystems. They block fish migration, alter water temperature and chemistry, trap sediment, and modify natural flow patterns. These impacts must be weighed against the benefits the dam provides and the historical value of preserving it. Climate change introduces new uncertainties into dam management. Projections suggest that Vermont may experience more frequent intense rainfall events in the future, potentially exceeding the design capacity of dams that were sized based on historical precipitation patterns. Sea level rise and changing weather patterns could alter the probability and magnitude of extreme floods. These considerations may necessitate further improvements to spillway capacity or other modifications to ensure continued safe operation. Conclusion: a monument endures. The Windsor Upper Dam stands as a testament to American engineering ingenuity, community vision, and the transformative power of infrastructure investment. For nearly 2 centuries, this modest earthen structure has shaped the development of Windsor, Vermont, and contributed to the broader story of American industrialization. From its construction in 1829 by Ithamar Beard and Windsor investors, through its vital role powering 19th-century mills, through its survival of Tropical Storm Irene, and countless other tests, the dam has endured. It has been maintained, rehabilitated, and adapted to changing needs and circumstances. It has outlived its original industrial purpose, but found new value in recreation, flood control, and historical preservation. The dam's story is ultimately a human story. It reflects the ambitions of early settlers who recognized that prosperity required infrastructure. It embodies the skill of craftsmen who built to standards that ensured longevity. It demonstrates the commitment of generations who maintained and preserved what their predecessors had created. And it challenges present and future generations to be wise stewards of inherited infrastructure, balancing preservation, safety, and environmental responsibility. As the Windsor Upper Dam enters its 3rd century of existence, it remains a functioning structure and a tangible connection to Vermont's industrial heritage. Whether it continues to serve for another century or is eventually removed and Mill Brook restored to its natural state, the dam has earned its place in the history of American civil engineering. It stands as evidence of what can be achieved when communities invest in their own infrastructure and commit to maintaining what they have built. The dam reminds us that engineering is not merely about technical calculations and structural designs. It is about understanding community needs, about building for longevity rather than expedience, and about creating infrastructure that serves multiple generations. The men who built the Windsor Upper Dam in 1829 could not have anticipated that their work would still be functioning nearly 2 centuries later, but their commitment to quality and their conservative approach to design made that longevity possible. In an era when much modern infrastructure seems designed for limited service life, when planned obsolescence often trumps durability, the Windsor Upper Dam offers a contrasting vision. It demonstrates that well-designed, well-built, and well-maintained infrastructure can serve for centuries. It shows that the initial investment in quality pays dividends across generations. It proves that careful stewardship can preserve even earthen structures against the relentless forces of water and time. The Windsor Upper Dam is more than a pile of earth and stone across a Vermont brook. It is a monument to human ingenuity, a testament to community vision, and a bridge connecting past to present. As water continues to flow through its gates and over its spillway, as the reservoir behind it reflects the changing seasons, the dam silently tells the story of a frontier community that built for the future and built to last. For nearly 200 years, the Windsor Upper Dam has stood watch over Mill Brook. If current stewards maintain the commitment to preservation that their predecessors demonstrated, it may well stand for 200 more, continuing to serve, continuing to endure, continuing to remind us of what is possible when communities invest in infrastructure that transcends the immediate moment and builds for generations yet to come.